The following presentation by Vittoria Laghi from the University of Bologna is cut a little bit short, so the beginning is not quite there. But once it kicks in, you'll learn about how topology optimization and additive manufacturing can create a new generation of green steel construction.
Being having more efficient structures, so supporting circular economy and also providing more efficient structural forms. So just to give you a little bit of an overview of some applications of what I refer to as additive construction with a little bit of metal in it. So when it comes to additive construction, most of the people just refer to this, which is actually unreinforced masonry units realized with concrete 3D printing. And to me, honestly, it's not maybe the best way of using 3D printing to create something that it's new and that can be achieved only with 3D printing and not with conventional manufacturing technologies. So I would be more interested in something like that. This is actually what it's called the dancing columns. It was actually a project of a couple of years ago from ETH Zurich. And this is to me the sense of using 3D printing to create something new, something not necessarily conventional, but out of the box. Not just in the sense of form, but also in the sense of material. So this is actually an example of earth 3D printing done by an Italian company, which is called WASP 3D, so that you can actually build with some other materials. And hey, you can also build with metal. So this is actually the first example of a large-scale metal 3D printing for construction, which I'm going to talk a little bit later about that. Hi, Thomas from MX3D here. So just to give you an outline of metal 3D printing in construction, the timeline is quite short. So there was just a little bit of applications almost 15 years ago, but mostly in academia, not really applied in real constructions. And when it comes to the scale of the elements to be printed, it increased only with the use of wire arc additive manufacturing, so large-scale metal 3D printing solutions. So this is actually the very first example. It was a facade node in aluminum made by powder bed fusion, and it was just an academic application. And the real first industrial application on metal 3D printing in construction comes with the Arup node. So it was actually a project done by Arup, which it was actually from the Amsterdam office. And it was a pity that it didn't actually, it never saw actually the light of a real application. But this one did. So there was actually the very first application to me of what it means to create something in metal 3D printing for a construction application. This was a footbridge realized entirely with wire arc additive manufacturing, stainless steel, with some new forms. During the same year, we actually also printed at the same facility with the same wire, but just a different deposition strategy. Also an entire column made in diagrid, which I'm going to talk about it a little bit later. Just to increase the size of the connections, this was another example of how big you can actually print, and you can actually use this for complex shaped joints, as for this case, this was for oil and gas application, or to create something completely new. So now we're moving towards topology optimization and metal 3D printing to create new construction elements and new structural forms that are efficient in this sense. Not just that, you can also do some sort of hybrid manufacturing in the sense that you can actually use the WAM to strengthen conventional pieces. So not just create something from scratch. And this is something that I actually saw by chance. I was in Hong Kong in November 2024, and I saw that in front of the governmental center, and it was okay, that is actually entirely printed in WAM. And I could stand just below this very cool pavilion. I'm not that tall, but it's almost 2 meters of height. So that's tall enough for me. But what is wire arc additive manufacturing? So to give you just an overview of that, it's honestly welding deposition strategy mounted on top of our robotic arm. So it's a sort of automatic welding deposition that creates something in metal 3D printing, just to give you very simple and practical definition of that. There are two different deposition strategies that can be used, the so-called continuous printing, which is a sort of an FDM, so layer by layer, but also dot by dot printing, so to create some lattice form and structures, so something new. Just to give you an idea of how many metal additive manufacturing processes exist out there, this is actually a report from AM Power, just to give you an idea. And wire arc additive manufacturing is also called wire DD, arc DD, like many other names, but it's just like a very tiny piece of that. But what's interesting is, especially for construction sector, this matrix to me. So the build versus cost, and actually, wire arc additive manufacturing is the best one for construction because we don't have that much money and we need to build big. So that's great. Just to give you an overview of other types of applications, just to see a little bit out of the loop, this was actually a propeller that was printed by Ramlab, a technology provider here in the Netherlands, many years ago, I would say 7 or 8 years ago now. This is another application. Some of the next examples are done by MX3D actually, which is located here in the Netherlands. These are furniture for an engineering firm in Japan that were entirely printed in stainless steel with the same exact process. But this also was printed with the same exact process, just a different deposition strategy. Also, this bike was printed with the same process. And also these art installations were printed with the same exact process. And similar process, but like from the same family, was also the use of this skyrocket that was entirely 3D printed. So just to give you an idea of how big you can actually print. So the first steps were, of course, coming from this very first case study. So it was great to me because at least it was the very first application of something like big and practical and applied for like a real construction, so a real structure. And the bridge is actually like 12 meters of span. And it was also the very first example of how far you can print, meaning like how free you can go with the form. So the advantages are, of course, that. So you can actually build with like free form. There are no geometrical constraints, either in the shape, but also in the size. But of course, there are still limitations. So there are no current regulations or certifications or guidelines for structural design. And there's still a little bit of lack of characterization of the material and the pieces to be printed. But we're getting there. So there's an increasing interest in this technology, especially with respect to others. So of course, like DED or WAM or like large-scale metal 3D printing is increasing in interest. But there are also current regulations that are out there for specific sectors, for example, oil and gas, and now also the construction. We're getting there slowly. So another question that I'm asked very often is this technology sustainable? So to me, sustainable is like a broad concept. So when it comes to environmental sustainability, it is sustainable as long as you are using it efficiently. So not to just achieve the same exact geometries as you could achieve with conventional manufacturing. So if you're creating something that is resource efficient and it's like optimized for the use, then it is sustainable, and there are proof of that. I'm also going to show it later. But sustainability for me is also from a societal perspective. So actually there are proof that by increasing the digitalization in such a sector, such as the construction sector, can also like improve the gender balance and also like achieve more sustainable society, to be fair. So yeah, our aim and our goal is actually to print something new and to create some new forms for a new generation of steel constructions. So in this case, these are just a few examples of that. So these are just from now on some case studies and ideas that we have been developed mainly at University of Bologna on how to integrate optimization with large-scale metal 3D printing for construction. The idea is this sort of integrated approach. I've also renamed it as blended optimization, just because we're not like really strongly going deep into like purely analytical topology optimization. We want to blend together many different aspects and many different inputs from different structural requirements, but also manufacturing constraints, and also honestly personal judgment from like the applications in the structural engineering. So the first example is a sandwich pipe, let's call it like that, sandwich tube, tubular sandwich cross sections. There are different names for that. Anyway, let's just think about like a jumbo structural cross section for which like you need very thick elements, very thick pipes. So the idea is that you need like that thickness to overcome local buckling or lateral pressure. So the idea is to actually recreate the cross section by creating this sort of like sandwich cross section. And we actually tested that, like validated numerically and also printed it. So yes, it is solid and valid. The other idea is actually in this case to combine not just optimization in the sense of the form, but also try to engineer the material. So this is actually like a more broader research. So I'm happy to actually like dig more into that if you're interested maybe later. But the idea is that we discovered like this sort of orthotropic behavior of the stainless steel material once it's printed. So the idea is to actually engineer and like use the different layer orientation to create like something that is stiffer thanks to this orientation and like this orthotropic behavior of the material, and achieve different structural solutions and like optimize the beams for each different orientation. And then like think about which one actually works best based on the orientation of the material. Not just that, we also applied like different load conditions and different support conditions to recreate some real life conditions, because in reality you don't really know like what the beam is going to be like under which type of load is going to be subjected. So again, we verified that, we tested, everything works, so that's great. Next one is the optimized joint. I'm really excited about this because actually like the grid shell from British Museum has always been like one of my favorite structure, but I also got into like knowing this not very well-known research in which like the engineer behind the conventional joints that were used for the grid shell were actually claiming like that it was, I wouldn't say a mess, but it was very hard to actually create these joints because they had to produce 1,566 different joints in CNC from solid plates. Imagine the amount of scrap that it was like created just to create these single joints. And imagine how it could have been, like how easier or let's say less material intensive could have been if we could have printed these joints. So we actually create an optimized version of that, which can be printed in WAM. And we also tested against like lateral buckling and everything. Honestly, like we aimed at reducing the material up to 80% without even accounting for the scrap coming from the CNC. And then we also like try to have like an environmental analysis on that. And we said, okay, just comparing apple with apple, so just comparing the manufacturing processes without even digging into the optimization and like how optimized the solution can be for WAM, what would be actually the footprint, the carbon footprint, just related to the process itself. And CNC is actually more like impactful with respect to metal 3D printing, just because it like for the scrap. Honestly, it was just a matter of material utilization. CNC can achieve a utilization of like 50%, whereas metal 3D printing can achieve a 95% of utilization. And not just that, of course, then if you are actually combining that with topology optimization, imagine how you can actually reach more sustainable goals. So not just in terms of environmental impact, but also from the economic point of view, because metal right now is kind of costly, so it makes sense to actually reduce the amount of that. Last but not least, this is another cool application. So we wanted to create something. I've seen like so many cool presentations about lattice material yesterday and today. So we wanted to actually, let's say, use the concept of lattice material, but in a structural form. So from structural perspective, lattice materials are actually like grid shells and truss structures, so something that we are kind of familiar with. But we wanted to actually create a version at the mesoscale, so at the scale of the single element. So we created something like as lattice elements, lattice structures. We patented this, so the design concept is actually to create an atomized version of the cross-section based on the solid pipe cross-section, in which it can actually achieve the same performances as for slender elements with a reduction of material use up to 75%. So that's great. And imagine if we were going back to the previous concept of how we can actually achieve like a greener solution. If you're reducing the material use, then it's going to be greener for sure and like more sustainable for sure. Not just that, of course, then we got into like this lattice ideas, and so we had fun creating like some cool shapes and forms. And then, okay, again, we printed the first concept in 2018, and then we started developing like other cool concepts and ideas. And we also developed a plugin for Grasshopper, which is called Lattice. So just feel free to download it if you're interested in. So what's next? So in the real world, how hard it is to go from like structural conventional pieces to freeform optimized 3D printed pieces. Like, what do we need to go like to, close this gap? So we took a survey, the same identical survey among like current generation and next generation of engineers. So honestly, like students from civil engineering courses and architectural courses and professionals. And we actually asked the same exact questions, like how familiar are you with the metal 3D printing in construction and in general, like the metal 3D printing processes. And it's fair to say that, of course, like the future generation are more interested in and more knowledgeable about the metal 3D printing processes, whereas current generation of engineers know it a little bit less. But then when it comes to bias analysis, you could tell that professionals said that they actually knew about metal 3D printing, but then they didn't even understand like or recognize the different single processes from one to the other. And the same goes for topology optimization. We also asked similar questions to topology optimization and how to recognize if a piece was actually optimized or not. And the response were actually very vague. So meaning that, honestly, there is an interest from current and future generations of engineers to apply these new technologies and, like optimization ideas and additive manufacturing for construction. But they need to be properly trained because they honestly don't know it yet. So this is also where our spin-off company goes. So we're trying to bridge this gap between academia and industry by actually just trying to apply large-scale metal 3D printing, not just in construction, but also in architecture, design, and other industries, and just to train them. So these are just some of the projects that helped us realize the cool things that I showed. And thank you. Hope to answer to your questions.
To learn more about the CDFAM Computational Design Symposium series, to see the archives of previous presentations, and to learn about future events, visit cdfam.com.